Elena wants to get to the bus stop as quickly as possible. The bus stop is across this grassy park, 2,000 feet east and 600 feet north of her starting position. She can walk along the edge of the park on the sidewalk at a rate of 6 feet per second and can travel through the grass but only at a rate of 4 feet per second. And we'd like the path that will get her to the bus stop the fastest. So as an optimization problem, the first thing we should really ask ourselves is, what is it that we're trying to optimize? And here we're looking for the fastest, so we're trying to optimize time. So we're going to be looking for a time equation. We have a picture here that's already labeled with x being kind of the distance horizontally across the park that she should walk across, and then down the sidewalk the rest of the way. So we are going to write an equation for time. And to do this, the time that it will take to travel is the distance that needs to be traveled divided by the rate. This is just kind of rearranging that rate is equal to distance over time. And so we have two different kind of distances with two different rates here. We've got the distance through the grass that has a rate of 4 feet per second. And then we've got the distance horizontally on the sidewalk, and that's really big. On the sidewalk, which is at a rate of 6 feet per second. So we're just going to add those two things together. So we have t equals, for this first part, this red portion, we know the rate is the 4 feet per second. But for the distance, we're going to find that by doing the Pythagorean theorem. We've got a triangle here, leg lengths of 600 and x, and then this distance is the hypotenuse. And so using the Pythagorean theorem, we can get that distance is the square root of x squared plus 600 squared, or 360,000. And then we have plus this blue portion here. And that distance is simply not the full 2,000, but 2,000 minus whatever that x is. So 2,000 minus x divided by the rate there on the sidewalk, which is the 6 feet per second. Okay, so this is the time that it will take Elena to travel if she chooses this x as the distance down that she should kind of aim for. So we're going to take the derivative of this. So t prime. Well, the derivative of this function here, this square root, we can think of as an exponent of 1/2. So we'll bring that down, and we'll combine it with the 4 to be a 1/8. And then we have x squared plus 360,000 to the negative 1/2. And then by the chain rule times the 2x. Okay. And then the derivative of this portion right here, well, the derivative of 2,000 is 0, minus x is a minus 1, and then over the 6. So this is the derivative. And because we are looking for the minimum time, we are going to set this equal to 0 and find what our critical numbers are. All right, so now our goal is to solve for x. I'm going to go ahead and do a little bit of algebra here. First, I will rewrite this as a fraction. We've got this negative exponent, which brings it down into the denominator. And so we've got an x in the numerator. The 2 and the 8 will cancel to be a 4th. Okay, and we'll put that in the denominator. So 4, and then root x squared plus 360,000. And actually, I'm going to now, I've got that thing, and I'm going to add a 1/6 to the other side of the equation. Okay, and now to solve, I'm going to go ahead and I'm going to cross multiply here just to get this in a little bit more workable area. So that gives me 6x is equal to, and then this thing times the 1. So 4 root x squared plus 360,000. Okay, now to solve for x here, I don't love that there's a square root here, so I'm going to go ahead and square both sides. So I've got a 36x squared equals 16, and then x squared plus 360,000. And now we will distribute this 16 into the parentheses. So we've got 16x squared plus, let's see, 16 times that is 576. Subtract the 16x squared from both sides. We get 20x squared equals 576, 0, 0, 0. Divide by the 20 from both sides, and we get x squared is equal to 288,000. And so x is the square root of that. X is the square root, 288,000. All right. Which, if we plug that into the calculator, is about 536.656 feet. Okay. We just need to double check that this is actually a minimum. So if we look at our derivative, remember, was this thing actually with the minus 6 there instead. Let me go ahead and just minus 6. That was the derivative. And so we're going to go ahead and just do the first derivative test with our t prime. We'll create a sign chart. We've got this 536.656. And we'll plug in a number on each side. If we plug in 0, that's a really easy one. If we plug in 0 here, this is 0, and then minus 1/6 is a negative. So that's a negative number. And then plug in a number larger than 536. And if we go really, really big, you'll see, that, of course, that this first expression, the larger x becomes the more negligible this 360,000 becomes, and this just approaches 1/4. And 1/4 minus 1/6 is a positive number. So for those large numbers, we'll get a positive, which means that this function is decreasing and then increasing, and so we've got a relative minimum at this number. And so that is the distance down that she should travel across the park to that point, and then the sidewalk the rest of the way.